Greetings! In this lecture, I will review ionic solids and focus on predicting relative melting points for ionic compounds. Ionic compounds are the second type of solid that we're considering. As you can see, I have space here for 5 types. Last time we did metallic. This time we're doing ionic, and ionic compounds have metal to nonmetal bonds, which you'll remember we term ionic bonds. Ionic bonds are non-directional. So here's a crystal lattice for sodium chloride, and each sodium cation is surrounded by 6 chloride anions. So we cannot reach in to a sample of sodium chloride and pull out a single sodium chloride molecule. Because of the way the lattice is arranged, there are 6 chloride anions surrounding every sodium cation. Therefore, we can't take a pair of tweezers and reach into the sample and pick out a single molecule of sodium chloride. It's an extended solid in 3 directions, and therefore this is called a compound and usually not called a molecule. Ionic bonds, of course, are governed by Coulomb's law, which is this mathematical equation that describes the electrostatic interaction between the positively charged cations and the negatively charged anions. Remember that Coulomb's law tells us that the force of attraction or repulsion depends on the product of this constant, the charges, divided by the product of the shielding factor times the distance squared. Of course, for ionic compounds, the charges, they could be +1 and -1, or +1 and -2, or +2 and -2, just depending on the charges of the ions in the species. Well, those charges would appear in the numerator of Coulomb's law. The size of the atoms would appear in the denominator as the distance. The smaller the atoms are, the closer together they can get, and so the smaller the interparticle distance. Those are the 2 factors that appear in Coulomb's law that affect the properties of this type of solid. If we wanted to melt an ionic solid and predict which solid had the higher melting point, we would have to consider this interparticle force. So the ionic compound is this 3-dimensional lattice of particles that have positive and negative charges, and those make the ionic bonds, which are non-directional. But it's important to note that all ionic bonds are relatively strong forces, and the stronger the force is, then what would you predict is true about the melting point? Would you predict something that has relatively strong interparticle forces would have a relatively high melting point or a relatively low melting point? Please go ahead and answer that now. Thank you for submitting your answer. The stronger the interparticle force is, the higher the melting point, because it will then be more difficult to allow those ions to move out of their lattice if we have a higher interparticle force. So one of the things you can think about if you look at Coulomb's law is the higher the absolute value of the product of the charges. In other words, product means we're multiplying these together. And if we have a negative charge and a positive charge, that's what happens in ionic compounds. So we have to take the absolute value of that so that we have a positive number. The bigger that number is, the higher the melting point, because that would be relatively strong interparticle forces. Let's review and say that a slightly different way. So when predicting the melting points of ionic solids, we need to look at the ionic bond strength, and that depends on 2 things: the magnitude of the charges on the ions and the separation of the ions. Both of those factors are found in Coulomb's law. Therefore, small ions, which have a small separation, so this would be coming in the equation as R, that are highly charged, and in other words, here I would mean +2 as opposed to +1 for relatively highly charged. Those have a higher melting point than ionic compounds which have large ions, and remember we know the periodic trend for atomic radii, that have relatively low charges. So, for example, some compounds are large cations, like rubidium, and it might have a relatively low charge. I would expect that type of ionic compound to have a lower melting point than an ionic compound made from lithium, which is very small and has the same charge. Here's an example. Which of these two compounds has a higher melting point? Magnesium oxide or cesium iodide? Please go ahead and try to answer that now. Thank you for submitting your answer. Hopefully, the approach that you took to this problem is applying Coulomb's law. Magnesium oxide has relatively small ions when compared to cesium iodide, and the magnesium ion is a +2 charge, and the oxide anion has a -2 charge. Cesium iodide, on the other hand, has relatively large ions. Again, that comes from the atomic radii trend. Those large ions have +1 and -1 charges associated with them. So if we look back up at the top, small ions that are highly charged have higher melting points. So I would expect magnesium oxide to have a higher melting point. If I look up the actual melting points, I see that magnesium oxide's melting point is almost 3,000 degrees Celsius. That's really high. So that was the correct answer. But I also want you to notice that cesium iodide's melting point is also quite high, isn't it? Most ionic compounds have very high melting points. Even the ionic compounds that we say are relatively low melting for being an ionic compound, because 626 degrees Celsius is still a very hot temperature. That's hotter than your home oven probably gets, unless you look at the burner on the stove. If you look inside your oven, you probably can't turn it up to such a high temperature. You'd have to buy a furnace to go to that type of temperature. Maybe you have a furnace at home. I shouldn't make assumptions. Let's end this lecture with a review example. Which of the following substances has the highest melting point? Krypton, beryllium oxide, carbon tetrabromide, potassium chloride, or barium fluoride? Please go ahead and answer this now. Thank you for submitting your answer. In order to answer this question, we would have to ask ourselves what types of solids these different materials would be. I've gotten a little bit ahead of myself because we haven't covered molecular solids yet, have we? Carbon tetrabromide and krypton are both molecular solids. Krypton's a noble gas. And just from the name of the group, that implies that it's a gas at room temperature and pressure. So it probably has a relatively low melting point below room temperature. So let's just cross that one off. Whenever I put that on a test, students have trouble with it. I think because of Superman and kryptonite. People like to say krypton's high melting, but it's really not. Carbon tetrabromide is not ionic. So we're going to cross that one off because that one has only intermolecular forces associated with the temporary induced dipoles. We'll talk about that more in the next lecture. So that leaves us some ionic compounds to choose from: beryllium oxide, potassium chloride, and barium fluoride. Which one of those has the highest melting point? Well, potassium chloride has a +1 cation and a -1 anion. Barium fluoride has a +2 cation and a -1 anion. Beryllium oxide is +2 cation and -2 anion. So just based on the charges, I would go with beryllium oxide. But before I answer for sure, I would want to think about the relative sizes. And I'm feeling pretty good about choosing beryllium oxide with that additional information because beryllium oxide also is relatively small ions. Fluoride here is the smallest, but oxide is almost as small, and barium, of course, is much bigger than beryllium. So the highest melting point is beryllium oxide. This concludes the second part of the introduction to solids, the examination of ionic solids and their melting points. We learned how to predict those relative melting points by going back to Coulomb's law, by using the monatomic charges and the atomic radii of the anions and cations.